Next, let's look at a couple of L'Hopital's rule problems. Here, this first one is 2a. Now, notice if we evaluate the limit of the top and we get 0. If we evaluate the limit of the bottom, we get 0. So we have this indeterminate case of 0 over 0. And that being the case, L'Hopital's rule tells us that we can go ahead and evaluate the ratio of the derivatives. So this is going to be 3 cosine 3x over 2 cosine 2x. So those two limits are the same. They're going to give us the same result. And now we can take the limit of the top, we get 3. The limit of the bottom, we get 2. We're just plugging in. So we get a limit of 3 halves. Now that was an indeterminate case of 0 over 0. Now we've got this one. And if we look at this limit, if we take the limit of what's being raised to a power, we get 1. And of course, the limit of x as x goes to infinity is infinity. So we have this case of 1 to the infinity. Now, you might not remember that that's one of the indeterminate cases. You don't have to remember that. The fact is, you don't know what that limit is. It's indeterminate for you. You can't tell what that limit is. So there's a process that we can use here. One of the things we would like to do is see if we can use L'Hopital's rule on this. So here's what we do. We just let y equal that limit, and then we take the natural log. And the reason we do that is because we would like to use that property of natural logs that will enable us to bring that x out front. Okay? So that's what I'm going to do. I have the log of y is equal to the limit as x goes to infinity of x log 1 plus 3 over x. Now with L'Hopital's rule, we need a top and we need a bottom. We need a numerator and a denominator. So I can just write this way. I can do this little trick. Instead of multiplying by x, I can divide by 1 over x. So let me put 1 over x down here. Now, notice, as x goes to infinity, the bottom goes to 0. As x goes to infinity, the top, we get log 1, that's 0 as well. So notice we have the case of 0 over 0. So now we know, yeah, I can use L'Hopital's rule on this. We might not have been sure about 1 to infinity, but if we can get it back in a form where we've got 0 over 0, or we've got infinity over infinity, we can go ahead and, use L'Hopital's rule. So here we go. We're going to take the limit of the derivatives. So the derivative up top, here we go. We got 1 over 1 plus 3 over x times the derivative of 1 plus 3 over x, which is negative 3 over x squared. And then the derivative of the bottom here, this is x to the negative 1. That's going to be negative 1 over x squared. Now notice that this minus here, we cancel. We've got 1 over x squared up top and on the bottom. So now dig what we have. We have the limit as x goes to infinity of this 1 over, that 1 over, well, it's 3. Notice we've got the 3 up there. 3 over 1 plus 3 over x over 1. See? Because this right here and this right here cancel. They divide it out. Now this made this look more complicated than it needs to. This right here, this term goes to 0. And what we're left with is 3. Now that's not the limit that we're looking for. That is the log of the limit. So we have to apply e to both sides and we get e to the third. That's our limit right there. Now let's look at some improper integrals. Now remember, when we talk about improper integrals, we have the case where infinity is in the limit of integration, like in 3a and 3b here, 3c down here. And then we have another type of improper integral where inside uh, the bounds of integration, the limits of integration, there's a infinite discontinuity. Like for example here, this 3D, we have the integral from 0 to 1, and obviously there is a vertical asymptote at 0. So there's no infinity in the limits of integration, but there is an infinite discontinuity there. So let's look at this first one. Now, remember the setup is we take the limit as um, b goes to infinity of 1 to b like this, see? So I'm just going to view it as a limit. Replace that infinity with b. Now, here's what we've got. We've got the limit as b goes to infinity of negative 1/2 x to the negative 2 from 1 to b. And what I did was I just used the power rule for integration there. So you took negative 3 plus 1, divided by it, and negative 3 plus 1 is in the exponent. So now let's see what we have here. We have the limit as b goes to infinity of negative 1/2 times 1 over b squared minus, now be careful, minus a negative 1/2 times 1 over 1 squared. Okay, I think I got that. A lot of negatives running around. But notice that this part right here, yeah, that's just 0 as b goes to infinity. So what we have then is we have a positive 1/2. That looks like what our limit is there. Okay, so there it goes. That is the value of that integral from 1 to infinity. Okay, now on this other one, here's what we've got. We've got the limit as b goes to infinity, 1 to b, x to the negative 1/2. And if you get the antiderivative, you've got the limit as b goes to infinity of, let's see here, there's going to be 2x to the 1/2 from 1 to b. Once again, I'm just using power rule for integration. So this is going to be the limit as b goes to infinity of 2b to the 1/2. Uh-oh, that's going to go to infinity. That's going to diverge. Minus 2. So this one right here, this goes to infinity. So this integral right here diverges. Okay, and we just stop right there. If any part of it goes to infinity, we stop. Now let's look at this next one. Okay, here we go. We've got the limit as b goes to infinity of, well, from 0 to b, 1 over 1 plus x squared dx. Now that antiderivative is going to be arctan. So what we have here is we have the limit as b goes to infinity of arctan x. Now remember, well, let me just go a step further. This is the limit as b goes to infinity of arctan of b minus arctan of 0. So this is just now, okay, so remember how arctan behaves. Arctan has horizontal asymptotes at pi over 2, negative pi over 2. So arctan goes like this. It behaves that way. So you can see, yeah, as b goes to infinity, this is just going to be pi over 2. That's the value. So that integral is just the result is pi over 2. Now I've chosen these ones because they, they're good ones to understand, or they give insight into similar problems. Notice that this right here, This is 1 over x to the p where p is greater than 1. This is 1 over x to the p where p is less than 1. Now remember when we said this, that when you have an integral like this, 1 over x to the p, remember we said that this integral will converge only if p is bigger than 1. So if you have x to the third, x to the fourth, and so forth. Over here, this is x is less than, this is x is raised to a 1/2 power. So that one diverges. Now, let's take a look at this one down here. Okay, so now we do this. We take the limit as a goes to 0 from the right. Okay. Now notice it's from the right, because if you look at this interval from a to 1, and if you're approaching 0, you're going to be coming from the right. Yeah. So let's see what this looks like. So we've got the limit as a goes to 0 from the right. And let's see, this is going to be 2x to the 1/2 from a to 1, like that. Now, if I put in a 1, I get 2 minus the limit as a goes to 0 from the right of 2a to the 1/2. And that part there is going to be 0, so it looks like I just get 2. Now, if that problem right there, notice here it's kind of the backwards of that what we just talked about with the p, 1 over x to the p. If you're talking about a vertical, or if you're talking about an infinite discontinuity, then this is not going to converge if p is bigger than 1. So it's, you want to be careful. What I said earlier is going to be uh, only when you have infinity in your limits of integration.